Hello, I'm Jenny Lynch, and this is the Creative Science Podcast.
Hi, I'm Matilda, and today's show is all about the science of electricity.
Sparks are going to fly with fascinating fast facts about electric charge, a deep dive into lightning, a question about the dangers of electricity, some ideas about how electricity is generated, and a truly shocking experiment for you to try yourself at home. Switch on your brain because here come 5 fun and fascinating fast facts about the science of electricity.
Fact number 1. Electricity is all around us, and even inside our bodies.
All the different things that electricity can do happen because of tiny things called electric charges. Electric charge is much too small for us to see, but we can see, hear, and feel some of the things that electric charge can do.
Fact number 2. There are 2 types of electric charge. There is positive charge and negative charge.
Opposite charges attract. So if there is a positive charge close to a negative charge, there will be a force of attraction between them.
Fact number 3. If 2 electric charges are the same, they do not attract. They repel.
If there are 2 positive charges close together, they will push away from each other. If there are 2 negative charges close together, they will also push away from each other. In other words, like charges repel.
Fact number 4. We are surrounded by positive and negative charges.
Atoms in the air have positive and negative charges. The floor has positive and negative charges. And even your body is made up of positive and negative charges.
Fact number 5. If an object has the same amount of positive and negative charge, we say it is neutral.
If an object has more positive charge than negative charge, we say it is positively charged. If an object has more negative charge than positive charge, we say it is negatively charged.
Let's take a deep dive into a spectacular example of electricity. Lightning. During a thunderstorm, high up in the clouds, positive and negative charges can be separated.
The top of a cloud will tend to have more positive charge, and the bottom of a cloud will tend to have more negative charge. As the charge builds up, there is a force of attraction between the negative charges in the bottom of the cloud and the positive charges in the earth. When the force of attraction is strong enough, electric charge can jump through the air, creating a bright flash of lightning. Lightning causes the air to heat up, so some of the electrical energy turns into heat energy. The heat energy causes the air to glow brightly, so there is heat energy turning into light energy. The extreme heat also causes a sound wave to be created, which we hear as thunder. So some of the heat energy turns into sound energy. The electric charge that moves through the air to create lightning tends to take the easiest path between the clouds and the earth. That means that lightning is more likely to strike somewhere very tall, like a tall tree or a tower. If you want to avoid getting hit by lightning, it's best to stay inside a building or a car during a thunderstorm and don't take shelter under a tree. If you're sitting inside a car when it's hit by lightning, you'll probably stay pretty safe from the electric charge. That's because the electric charge will move through the metal parts of the car to take the easiest path to the earth, and the inside of the car will remain lightning-free. As well as charge jumping between clouds and the earth, lightning can strike high up in the clouds when electric charge jumps between clouds or even inside large clouds, jumping from one part of the cloud to another.
Now it's time for a question. How dangerous is electricity?
Electricity can be extremely dangerous and even deadly. That's why children are taught to stay away from power points because they could get a deadly electric shock. However, not all electricity is dangerous. Inside your body, there are electrical signals in your nerves that communicate information between your brain and other parts of your body. If you've ever felt a small static electric shock, you'll know that it might not feel very nice, but it certainly won't kill you. Static electricity can build up in everyday situations like jumping on a trampoline, walking on carpet in slippers, or drying clothes in a tumble dryer. Most handheld electronic devices use low voltage DC power, which is a lot safer than the higher voltage AC power that is inside a power point. DC stands for direct current, and AC stands for alternating current, and it describes how the electric charge moves in an electrical circuit. When you plug in an electronic device into a power point, you'll probably have a chunky plug, which is a transformer that turns the higher voltage AC power from the power point into the lower voltage DC power that's used by the device. Batteries, like the ones you might use in a torch, use direct current. And you might have noticed that a battery has a positive terminal with a plus sign and a negative terminal with a minus sign. You have to make sure the battery is inserted with the positive and negative terminals the right way around, otherwise the electricity won't flow in the circuit and the torch won't work.
People have been aware of electricity for thousands of years from experiencing static electricity in their day-to-day lives. But they weren't necessarily able to explain what causes static electricity.
In the 1700s and 1800s, scientists made huge advances in electricity and magnetism by experimenting with electric charge and magnets and trying to explain how they work. The scientist Michael Faraday did experiments with electricity and magnetism that led to an understanding of how to generate electricity. And before too long, electricity was being used to generate light in people's homes. The first electricity generators worked by moving a magnet inside a coil of wire. The magnetic field caused electric charge in the wire to move, creating an electrical current. Nowadays, we have electric turbines, which work on the same basic idea that a moving magnetic field can generate an electrical current. To use a turbine to generate electricity, you need to get the turbine spinning. One way to do that is using steam. Most of the electricity used in Australia is generated in coal-fired power stations. Coal is burnt to make heat energy. The heat energy warms up water to make steam. The steam forces the turbine to spin, and the moving energy in the spinning turbine turns into electrical energy. Gas-fired power stations work in a similar way, but they burn gas instead of coal. Flowing water can also be used to spin an electric turbine, and we call this hydroelectricity. A wind turbine is an electric turbine that spins under the power of the wind. For solar-powered electricity, solar panels collect light energy from the sun and turn it into electrical energy that can either be used straight away or stored in batteries to use later. Electricity generated using water or wind or solar power is called renewable, because these sources of energy aren't used up in the process of generating the electricity. Coal and gas are both non-renewable sources of energy because planet Earth has a limited supply of these fuels. Also, burning coal and gas makes carbon dioxide gas, which is the major cause of global warming and climate change. Increasing the amount of electricity that is generated using renewable sources of energy will mean that we can use less coal and gas to generate electricity. That means less carbon dioxide going into the Earth's atmosphere, which will help to slow down global warming and climate change. Static electricity is generated by the force of friction. When two objects rub together, electric charge can move from one object to the other, causing a build-up of positive charge on one object and negative charge on the other object. The transfer of electric charge depends on the type of material in each object.
You can test this out yourself. Of course, you should tell an adult what you are doing and make sure you get their permission first. You'll need some paper, torn into small pieces, and a balloon.
Sprinkle the pieces of paper on a table. Blow up the balloon and rub it on your hair to charge it up with static electricity. By rubbing the balloon on your hair, you're moving around some electric charge. Some of the negative charge from your hair is moving onto the balloon, so the balloon will have a negative charge. Hold the balloon close to the pieces of paper and watch what happens. Does the paper jump onto the balloon? The negatively charged balloon is surrounded by an electric field. The positive charges in the pieces of paper are attracted to the negative charges on the balloon, causing them to move. Some animals can feel electric fields using a specialized sense called electroreception. Sharks can sense tiny changes in electric fields made by the muscles of their prey. When fish swim around, their muscles give off electrical signals that can be detected by the electroreceptors in the nose of a shark. This adaptation is used by another fierce predator, the platypus. The platypus feeds underwater with its eyes and ears closed, and it finds food by sensing tiny electrical signals in smaller animals like fish and shrimp so it can catch them and eat them alive. Honeybees can sense electric fields too. Honeybees use their electroreceptors to find flowers and collect pollen. A flower can be surrounded by an electric field, which is sensed by a bee as it flies close to the flower. When the bee gets close enough to the flower, pollen grains are attracted to the bee and jump onto the bee and get stuck, a bit like the pieces of paper jumping onto the balloon. Isn't that unbelievable? Now that we've sparked your interest in science, it's time for us to go. Thanks for listening, and remember to stay positive. Stay curious.
Creative Science Podcast was recorded on the traditional lands of the Bidjigal people. For more information about Creative Science Australia, visit creativescience.com.au.